In complexity theory, we often talk about problems in P and NP. In addition, there's another important class of problems called NP-complete. However, you might be wondering, what exactly is NP-completeness? We often talk about NP-completeness to relate the difficulty of multiple problems to each other. First, we'll define what makes a problem NP-complete. First, for a problem to be NP-complete, the problem must be in NP. That is, the problem must be verifiable in polynomial time. If we were given a witness to our problem, could we verify that witness is a valid solution to our problem in polynomial time? For review, let's discuss what is a witness. A witness to a problem is a theoretical concept where we are simply given a solution to a problem. We don't know how it was computed. All that matters is that we know that our witness is a solution to our problem and we can use it to verify its correctness. I would like to make one final note. The formal definition of a problem being an NP is there exists a non-deterministic Turing machine that decides a problem in polynomial time. In this video, we will use our original definition that we defined for NP for simplicity. Furthermore, for a problem to be NP-complete, it must be NP-hard. For a problem to be NP-hard, there must exist a polynomial time reduction to a problem that is NP-hard. That is, if x is a solution to our current problem, then its transformation must be accepted by m. Similarly, if x is not a solution to our current problem, then its transformation must not be a solution to m. We define our transformation function as f of x, where x is an input in L, and f of x returns an equivalent input in m. Let's go into greater detail about the idea of reduction. On the left, we have all of our inputs in L. On the right, we have all of our inputs in M. We will divide our set of inputs in M into two sections. At the top, we have all of our inputs that are accepted by M. At the bottom, we have all of our inputs that are rejected by M. Let's say we have an input in L labeled x. In this case, x is considered a good input. Therefore, after we transform our input, our newly transformed input will be mapped to the top section of M, where the top section of M is the region of good inputs. Let's say we now redefine x to be a bad input in L. Then our transform input will be mapped to the bottom section of the set of inputs in M, thus also being a bad input. In this video, we'll be discussing some problems in the family of the three coloring problems and prove that they are NP-complete. First, we will prove that the three coloring problem is NP-complete. Next, we will prove that the planar three coloring problem is NP-complete. After that, we will prove that the max degree 4 three coloring problem is NP-complete. And finally, we will prove that the planar max degree 4 three coloring problem is NP-complete. For those that might have taken combinatorics in your college curriculum, you might have learned about the chromatic number of a graph and its coloring. For those unfamiliar with the concept, the chromatic number of a graph is the number of colors that it would take to color the graph, such that no two adjacent vertices are the same color. For example, let's say we color A to be red. And since B is adjacent to A, it needs to be a different color. So in this case, let's say we choose blue. And then finally, since C is adjacent to A and B, we have to color it green. And finally, we can choose D to be red or blue. We'll choose it to be red. Here, we have shown that there's a three coloring for this graph. Let's look at another example, an example that might not necessarily have a three coloring. First, let's color vertex A to be red. And furthermore, since B is adjacent to A and A is red, let B be blue. This leaves us with C being green. And now, when we do try to color D, it's adjacent to three different colors. But since D can be only one of the three colors, there's no way that we can three-color this graph such that it's three-colorable, and thus this example is not three-colorable. Now, let's prove that the three-coloring problem is an NP. We will define our witness to be the color of each vertex in our input graph. Now, given this witness, how can we verify our input graph is three-colorable? We know that a graph is three-colorable if all of its adjacent vertices have a different color. Therefore, we need our algorithm to run such that it iterates over all the vertices in the graph and checks if its adjacent vertices are a different color. One algorithm that can do this is BFS. We'll run BFS, and as we visit new vertices, we'll check if its color is different than the current vertex's color. First, let us define a function called verify, where our parameters are our input graph G and our witness W. Next, we will create an adjacency map, where we'll map each vertex to its adjacent nodes. We will also define a visited set, so we can keep track of all the vertices that we have visited. Next, we will iterate over each vertex in G to make sure we BFS over each component. And if we have not visited that vertex yet, then we have a new starting point. We will then initialize our queue and then add our new starting point to the queue. And then while we still have vertices in our queue, we will let n be the size of the current level. and then we'll iterate over each vertex at that level. We will then pop the current vertex at the top of the queue, and then if we have not visited this vertex yet, then we will add this vertex to our visited set. Next, we'll iterate over each adjacent vertex to our current vertex, and if in our witness the adjacent vertex is the same color as our current vertex, we will return false. We will then check to see if the adjacent node has been visited, and if it hasn't been visited, we'll add it to our queue, and then finally, we'll have our function return true. Let's analyze the runtime of our function. First, we build the adjacency map, which we know takes linear time in regards to the number of vertices and the number of edges. Next, we will BFS over each component. We know that BFS runs in linear time with regards to the number of vertices and the number of edges. Therefore, our final time complexity is linear and polynomial. Therefore, since our function runs in polynomial time, we have shown that the three-coloring problem is an NP. I'd like to also note, in the case that the graph is sparse, it might be the case that our verified function runs in quadratic time, but it's still polynomial, so it doesn't matter. Next, we will show that the three-coloring problem is NP-hard. To do so, we'll be performing a reduction from the 3-set problem. If you are unfamiliar with the 3-set problem, I would recommend doing research on it prior to watching this part of the video. We define a formula in 3-set to be a list of clauses which are all ANDed together, implying that each clause must be true. Furthermore, for each clause in 3-set, we can have at most 3 variables, and in order for the clause to be true, one of the literals have to be true. We'll let true be defined as the color blue, and then we'll define false to be the color red. First, let's look at the case of two literals. We will create a gadget to simulate an OR gate. We want our OR gate to output blue if either inputs are blue, and red if both inputs are red. Let's say in this case, xj is blue and xk is red. Since we want the output to be blue in this case, that means we have to make the vertex adjacent to xj to be red, and then we have to make the vertex below to be green. Notice how this OR gate is also 3-colorable and also satisfies the property that we needed. Let's look at another case. This time xj will be red and xk will be blue. Since we want the output for this case to be blue, this implies the node next to xj must be green, and then the one below it must be red. And therefore, we have the correct input and it's 3-colorable. Now let's look at the case where xj is also blue and then xk is blue. We note that the output for this one also needs to be blue. This one we can see easily. If we want to 3-color this little graph, then we can just simply make the top red and the bottom green. Let's say now xj is red and xk is red, and let's say somehow we try to output blue. However, this would be impossible, so the only output that we can have is red. And next, we can just 3-color the middle layer using blue and green. So you might be wondering, well, there also might be a third literal, so how exactly do we factor this in? Well, we'll modify our gadget to accommodate for this. Here, as you can see, we have 2 OR gates like the ones we mentioned previously. We take the input from one of the OR gates and use it in another. Furthermore, we're forcing the end of the OR gates, right, the final input, to be blue. If it's red or green, then it will not be 3-colorable, and thus the input will be invalid. Therefore, we can see, if one of the literals is set to true, then that means this graph will become 3-colorable, and else it won't. Now, let's say we have 2 clauses. Well, we can connect them as follows, right? And then furthermore, let's say we have n clauses, right? Then we can follow this idea through, and we can create even a bigger graph. Now, you might be wondering, okay, well, how do we see the correlation here? Well, we can see that if at least one of the clauses is set to false, then one of the subgraphs will not be 3-colorable, and thus the entire graph will also not be 3-colorable. And since we iterate over each clause to make this reduction, we know that it takes polynomial time. Next, we'll prove that the planar 3-coloring problem is NP-complete. To show that it's an NP, we can use the same algorithm that we used in 3-coloring, since a planar graph is just a graph itself. Next, we'll prove that the planar 3-coloring problem is NP-hard. To do so, we'll reduce from the 3-coloring problem that we just proved was NP-complete, and then we'll use that to show that the planar 3-coloring problem is NP-complete. Let's look at this graph for example. Clearly we can see that it's not planar because we have 2 edges crossing, right? So what kind of gadget can we create such that its colorability is preserved? That is, if it was not colorable before, we don't want it to become colorable and vice versa, but also we want it to become planar. Well, we'll create a gadget called a crossover gadget. So now we can utilize this crossover gadget to eliminate crossings, right? So for example, in our example graph, we can get rid of the two edges that cross together and then replace it with our crossover gadget. Now let's look at the bigger picture, right? We figured out, okay, how we can make a graph that was previously not planar, and then we can replace each crossing using this gadget, right? So the first big idea is we're going to find out which edges cross together, and if they do cross together, we use these crossover gadgets to basically eliminate those crossings, and therefore we make our input planar. It is also important to note if there are two or more edges that are crossing each other, we might also have to use subdivisions, such that we can use these crossover gadgets to make our graph planar. Now, let's go into the three colorability of our gadget. The key idea behind our crossover gadget is that it can only be colored in two distinct ways, disregarding the permutation of the colors. One of the ways it can be colored is as follows. The following is also another way that we can color our gadget. There's one more important caveat that we need to address. Let's look at a crossing that consists of two edges and four vertices. Let's say to eliminate the crossing, we just set each end of our crossover gadget to be directly connected to the vertices. However, there's an issue with our current setup. Recall that y in and y out must be the same color. Therefore, this would imply that both vertices were the same color prior to using our gadget. However, if they were the same color, then it would imply that the example was not three-colorable. But by how our gadget works, it would be three-colorable, which we knew wasn't the case before. So we need to add a small modification to fix this issue. We will add an additional node and edge connected to X out and Y out. It might take some time to understand why exactly this works, but think about the properties of the crossover gadget that we previously mentioned. Therefore, our transformation will now be consistent. With regards to the runtime of reduction, we know that we need to iterate over each edge and check if it intersects with the other edges in the graph, which, at a high level, we could see it would run in polynomial time. Next, we will prove that the max degree 4 three-coloring problem is NP-complete. Similarly to the last two problems, since our input for max degree 4 three-coloring is just a specific type of graph, we can use the same algorithm that we used to show three-coloring is an NP to show that max degree 4 is also an NP. To show max degree 4 three-coloring is NP hard, we will reduce from the original three-coloring problem. Since we know that the max degree of vertex can have is 4, we need to create a gadget that can help us modify vertices which have degrees greater than 4. With this gadget, we have three ends that we can use to connect to other vertices. Furthermore, the design of our gadget allows it to always be three-colorable if each of the three ends are the same color. Now, you might be wondering, our current gadget can only replace vertices that have degree less than or equal to 3. So, how can we modify our gadget to account for this? Well, we can combine multiple copies of the gadget together to accommodate for the number of inputs that we desire. So in this case, if we combine two gadgets together, now we will have 4 inputs that we can use to connect edges and vertices together. Let's look at an example that implements this idea. In this example, our graph already satisfies the criteria of having a max degree of 4. However, we will still use it to demonstrate how our gadget works. Notice that this graph is three-colorable. Furthermore, let's say we want to replace the middle vertex, which is red, with the gadget we designed. Since the middle vertex had a degree of 4, we need 2 of our gadgets connected together to replace the middle vertex. Now, we can connect each vertex that was originally connected to the middle vertex to the ends of our new gadget. Notice that this graph is also three-colorable as well. With regards to the runtime, our reduction would run in polynomial time since we would iterate over each vertex and check its degree. If it is greater than 4, we would create the appropriately sized gadget and replace it with the current vertex. Now we will prove the final reduction of this video. We will prove that the planar max degree 4 three-coloring problem is NP-complete. Since our input for the planar max degree 4 three-coloring problem is simply just a graph with structural constraints, we can use the algorithm we used to show three-coloring was an NP to also show planar max degree 4 three-coloring is also an NP. For our reduction, we will reduce from planar three-coloring. Since we need each vertex to have a max degree of 4, we can use the same gadget that we used to show max degree 4 is NP-complete. With regards to the runtime, since we know it takes polynomial time to add our gadgets in the max degree 4 problem, then we know in our current reduction it will also take polynomial time as well. Therefore, we have shown that the planar max degree 4 3-coloring problem is also NP-complete. Now that we have proven some problems that are NP-complete, let's look at the bigger picture. What does this all mean? What does this tell us? When we discuss the classes NP, P, and NP-complete, we can diagram them as follows. We know P and NP-complete are subsets of NP, but what does this show? Let's briefly dive into the NP-complete class. Here, we have a tree of some of the proven NP-complete problems. The most important of them all is the SAT problem, which was proven to be NP-complete by Stephen Cook and Leonard Levin in 1973. Essentially, all the problems in this tree are the same except their inputs have been transformed to match a certain criterion. Think about it as molding the input into a different shape for each problem, even though the material just remains the same. So, how does the relationship between P and NP influence NP completeness? Let's say we found out that P equals NP. This would imply that SAT has a polynomial time algorithm to solve it, and as a result, the entire NP completeness tree would collapse. Algorithms that we consider to be NP complete would all have polynomial time algorithms to solve them, allowing us to solve them more efficiently. Now, what if it was proven that P does not equal NP? Well, this would imply that problems that are NP complete do not have efficient algorithms to solve them, therefore solidifying the NP completeness tree. At the very end, NP completeness is dependent on the big question. Does P equal NP? We don't know, and probably never will. However, it is a fascinating idea to know there exists a class of problems which are equally as difficult. And if one of the problems were proven to be efficient, then the whole NP completeness class would cease to exist. I hope you enjoyed this video, and I hope you gained more insight on NP completeness. I found the topic to be interesting, so I hope you did as well.